Okay, welcome to your second video lecture in section 10.4 on even and odd functions. Okay, so when solving problems in differential equations, it's often useful to take a function f that is originally defined in a small interval 0 to L and expand it so that it is a periodic function with period 2L so that we can expand it in a Fourier series. There are multiple ways to do that. We'll do two ways in this lecture. The first way is to create the even periodic extension of f, which basically takes f and reflects it about the y-axis. So it takes the original f from 0 to L, reflects it about the y-axis, and then makes it 2L periodic thereafter. The function's even, so its Fourier series will be a cosine series. So say, for example, we have the function f of x is equal to x here on the interval 0 to 1. This is just the straight line we're accustomed to. The even periodic extension reflects this line here about the y-axis and then proceeds to make the function 2 periodic thereafter. So notice every 2 units this guy repeats itself. Once we have this extension, what we can do is find the function's Fourier series. So we extend it to -1 to 1, and we know that since it's even, only the cosine terms will be non-zero. We go ahead and find those terms using this integral here. Notice again we're only integrating from 0 to 1 because it's even. We multiply that by 2. We end up with this expression, which is 0 when n is even, right? Because this term is going to be 1 when n is even, canceling with this -1, and these are all going to be 0 because sine of multiples of pi are all 0, and it's going to be -4 over n squared pi squared when n is odd, because this term is going to make a -2 times this 2, so that'll be -4, and then over n squared pi squared, and then with the exception when n is 0, you can actually find that a naught will be 1, so just take the integral from 0 to 1 of x, that'll give you a half, multiply by 2, that gives you 1. And so what you have here is this Fourier cosine series, okay, which really nice. This is just 2 terms of the cosine series. The only place where it has issues are these 2 endpoints, and really they're not that big of errors there. So you really only have to take the first 2 terms of that cosine series to get a good approximation of the function x over the interval 0 to 1 here. Another way to expand a function in a Fourier series of period 2L is to create the odd periodic extension, which, much like the even one, takes the function as is from 0 to L. In this case, to make it odd, what we need to do is make it 0 at both 0 and L, and then it reflects it about the origin from x going from -L to 0, and then of course makes it 2L periodic. This function is odd, and therefore its Fourier series will be a sine series. So again, with our function f of x is equal to x on the interval 0 to 1, if we make it an odd function, what we end up with is this result here, which again is 2 periodic, as that repeats itself every 2 units. It's also odd, as it's reflective about the origin there. And so for our example of f of x is equal to x, if we take its odd periodic extension, what we'll end up with is the need to find the bn's, the sine coefficients in the Fourier series. If we do that, again, because x is now odd, sine times an odd function is an even function. We'll again have the integral from 0 to 1 and then twice that integral. What we end up with is this expression, which reduces down here to -1 to the n plus 1 times 2 over n pi. Notice these terms are actually bigger because the n and the pi are to the first power in the denominator, so it's going to actually take longer for this guy to converge. And that's exactly what we see when we look. This is actually for n is equal to 10. We have n is equal to 10, what we're going to have is issues here at these discontinuities. So if you remember the last graph, there was a discontinuity that started here that wasn't in the even extension, because the even extension just had the graph go down from there. And so the sine functions, which again are continuous, are going to have difficulties there trying to both wiggle, be continuous, and model a discontinuity there. So what's interesting here is that we have the same function. We do an even periodic extension, is that we have a very easy task of approximating it with an even a cosine Fourier series. But if we try an odd periodic extension and we try the Fourier sine series, we have a difficult time approximating this function. Okay, thank you.